10 scientists connected to advanced propulsion research have died or disappeared between 2023 and 2026. The FBI is investigating. This investigation is not about the people, it's about what they were working on. Because at the center of this story is a material so important that it helps determine what engines can fly, how long they can survive, and who controls the future of propulsion. To understand why, we have to go inside the metal. Most metals weaken when temperatures become extreme. This one was designed for exactly those conditions. A nickel superalloy can operate at temperatures that would destroy ordinary steel, while carrying enormous mechanical loads. Inside every modern jet engine are components made from materials like this. Without them, modern aviation would look very different. And the newest versions are pushing performance even further. The difference between success and failure isn't hundreds of degrees. Sometimes it's 50, sometimes less. A small increase in temperature capability can mean longer engine life, fewer failures, lower costs, and dramatically improved performance. That's why engineers spend years chasing improvements that look insignificant on paper. Because in propulsion, small numbers can change everything. Most people think the value is in the alloy itself. It isn't. The chemistry can often be studied, patents can be read, research papers can be published. The real secret is usually the process, how the material is made, how it's treated, how it's cooled, how it's transformed from a formula into a working component. That's where the advantage lives. These are in concession. A better turbine material doesn't just improve a rocket engine, it affects launch costs, engine reliability, military propulsion systems, hypersonic research. Entire industries can move because of improvements measured in fractions of a millimeter and a few degrees of temperature. The material looks small, its consequences are not. Hypersonic research. This is why nations invest billions into advanced materials research. Because whoever controls the manufacturing knowledge controls the capability. And capability creates leverage, not just in aerospace, in defense, in economics, and increasingly in geopolitics. The competition isn't slowing down, it's accelerating. Here's the part most people never see. Two laboratories can start with nearly identical materials and produce completely different results. One component lasts, the other fails. The difference isn't always the chemistry, it's the process. Years of testing, years of refinement, years of learning exactly what works. Knowledge that cannot be copied simply by looking at the finished product. The alloy itself is not the mystery. The manufacturing knowledge is. Knowing a material works is valuable. Knowing how to make it work consistently, at scale, every single time, that's worth far more. Because that's the difference between a laboratory breakthrough and a strategic capability. This story was never really about a piece of metal. It's about what happens when engineering becomes strategically important, when materials science becomes national security, when a microscopic structure inside a turbine blade starts influencing decisions far beyond the laboratory. That's where this investigation leads. The metal doesn't care about patents. It doesn't care about governments. It doesn't care about investigations. It obeys only physics, heat, stress, time. Everything else is human. And that's why understanding the material is often easier than understanding the people around it. LEMEESEEDEM. The investigation never ends.